All right, let's begin studying algorithms. And here in this first lecture, I want to focus on a very standard algorithm for sorting things known as bubble sort. There's a good chance that you've learned bubble sort in a previous course, but even if you haven't, it's really a very straightforward method for sorting say numbers, but it could be used to sort other kinds of data, strings or any kind of data that for which an order makes sense. But we'll stick to sorting numbers. So for a little while we're going to stay focused on this problem of sorting of numbers in increasing order and compare different algorithms for doing that. So as I say, we'll begin with bubble sort. It's simple. It's basically among the easiest to understand, and it's perhaps of the various standard ways of sorting, it is actually the worst performing algorithm. Okay, it does slightly worse than two others that we're going to take a look at after bubble sort, immediately after bubble sort. And as the list gets long, it does much worse than algorithms we're going to look at later. An example of sorting using bubble sort. So here we begin with an array of 6 numbers. Okay, we've got the number 63 in position 0, 17 in position 1, 92 in position 2, 5 in position 3, 72 in position 4, and 21 in position 5. Now, I'm going to do something that people argue about, but frankly, I'm going to do it my way. The number 63 is in position 0. Some people prefer to refer to that position as the 0th position. I do not. I call position 0 the first position. I call position 1 the second position. Personally, it just feels more natural to me. So anyway, here's how bubble sort begins. The first two numbers are compared. So in this case, the first number is 63 and the second number is 17. We immediately see that they are not in the correct order. Okay, again, we're trying to sort this array so as to end up with the numbers going in an increasing order, and therefore we want the 63 to come after the 17. Okay, so observing that 63 and 17 are not in the correct order, what we do is we swap them. They change places. The 17 goes into the first position and the 63 goes into the second position. Okay, then we move on and compare the second and third positions. So at this point, 63 is in the second position and 92 is in the third position. We observe that they are in the correct order. 63 is less than 92, so we leave that alone. We don't swap and we move on. So next we compare positions, well, the third and the fourth entries. That is, we're looking at 92 compared to 5. They are not in the right order, and therefore we swap again. Okay? Okay, so at this point, we're looking at 17, 65, 92, 72, 21. Okay, but we continue. Go on to the fourth and fifth entries. So that is 92 compared to 72. They are in the wrong order, so once again swap. And then go on to the fifth and the sixth entries, the last two entries. Since they are not in the correct order either, we've got one more swap here. Okay, so there it is. Well, there what is. It's clear from looking at this thing that we have not sorted the array. However, but clearly we made improvement. When we look at what happened after a single pass through the array, we guess that while the array may not yet be sorted, we've somehow moved in the right direction. We're getting closer to having a sorted array. A very important fact is that after the first pass, it's guaranteed that the largest number in the array, in this case 92, will have moved to the last position where it belongs. Okay? All right, so let's see what happens in our example if we now go back and take a second pass through the array. I won't show you all the details, but we would end up, after the second pass, in this situation. And the thing to notice now is that 72, which is the second biggest number, has moved to the correct position, to the next to the last position. So we actually have the last two numbers being the biggest two numbers as we want. Okay? So let's think about what happens after a third pass. If we take a third pass through the array, then the third biggest number, 63, will have moved to the correct position, and we'll have the last three numbers being the biggest three numbers. Well, in fact, we wound up after three passes with a sorted array, but frankly, that's an accident. We got lucky. It only took three passes to sort this array, but we should ask ourselves, in general, how many passes would it take to guarantee that the array is sorted? Okay, so let's think about that. Here are some important facts. In general, it's going to take 5 passes to sort an array of size. Okay? More generally, if we have an array of size n, it could require as many as n-1 passes. But we're guaranteed that if we take n-1 passes, the array will be sorted after that. Okay? Also observe that each pass is not required to go as far as the previous pass. Each pass can stop a little bit sooner than the previous pass. Okay? Here are the specifics on that. Yeah, so if we're going to sort an array of size n, then the first pass is going to take n-1 comparisons. Okay, go back, I urge you to go back and check our example where n was 6, and you'll see that that first pass entailed 5 comparisons. Okay? The second pass takes n-2 comparisons. So in the example, that would be 4 comparisons. A third pass, in general, requires n-3 comparisons, and so on, until you get to the last pass, which is the n-1 pass, and then you'll see that all that's required during that last pass is to do a comparison of the first two numbers. Okay, a single comparison is all that's required on the last pass. Okay? Well, once again, when I say first position, I'm talking about position 0 in the array, and second position, I mean position 1 in the array, and so forth. Okay, now I want to turn to some actual code, by which I mean C++/Java code. It's actually old-fashioned C language code, and as I've said in the introduction, the reason for trying to teach this course and look at actual code and try to teach it to both a Java and a C++ class simultaneously is that there is this great commonality of the two languages, both being derived from this older language called C, and both having object-oriented features and things like that, but mainly because they're both so-called C-based languages. So when I present code, I try very hard to present code that will be exactly the same whether it's in C++ or Java context. And later on, when things get a little more complicated, I vary from that slightly, I will draw attention to the differences. But remember now that there's code provided in the course. All the examples, there actually are corresponding running programs that you can download, and there's a C++ version and a Java program, Java version, and I absolutely encourage you to take a look at the code that's appropriate for you. Okay, so here we go. Well, this is it. This is all the code that's required to implement bubble sort. As the previous slide indicates, the variable size, S-I-Z-E, we're presuming to have already been set, and it's the number of numbers that we want to sort. So size here is what we were previously calling n, the number of numbers to sort. Okay? This code consists of a nesting of two loops. There's an outer loop, which uses I as an index, as a loop counter, and an inner loop that uses j as a loop counter. Okay? Inside both of those loops, there's a conditional statement that basically says if two consecutive entries in the array are out of order, then we need to swap them. Okay? We need to interchange them. Okay, well, the swapping is relatively easy. You probably learn this idea in an introductory course in programming. If you want to interchange two things, two entries in an array, say, what you have to do is take one of them and copy it to a different variable. So that's why I have this variable temp here. Temp is used to hold the value that's stored in position j-1 of the array temporarily. Okay. And then the entry in position j is copied into position j-1, and then the number that we stored in temp, the old array j-1, gets copied into position j of the array. So the upshot of those three statements that we've effectively interchanged the contents of array bracket j-1 and array bracket j. Okay? All right, so that's it for the inner guts of this thing. What about the outer loops? Well, I'm practically certain that you're already bothered and perhaps annoyed by the absence of curly brackets for these loops. I'm deliberately not using them. They are optional in this example. Okay? So if it makes you more comfortable, put them in. So what I mean is take that inner loop. The inner loop says for int j equals 1, semicolon j less than I, semicolon j plus plus, you're certainly allowed to follow that by a pair of curly brackets and put the next 6 lines inside those curly brackets. Okay? And likewise for the outer loop, for int I equals size, semicolon I greater than 1, semicolon I minus minus, you can follow that loop header with a loop body that involves curly brackets, and then you put the inner for loop inside those curly brackets. Okay, and that's probably how you're trained to do things. I'm deviating from that. And the fact is, I want you to learn that curly brackets for loop bodies are not always required. Okay? And frankly, I think you need to get used to that. Even if you like them when you write your own code, you need to recognize when you read other people's code, if they don't use the curly brackets, you still need to be able to recognize what the loop body is. And one would hope, and certainly it's always my practice, to indent the bodies of loops to make it clear what the loop body is. Okay? So I'll say it again. The outer loop has a loop body which is exactly the inner loop. And the inner loop has a loop body which is exactly that if statement. And the if statement constitutes the last 6 lines here. 1, 2, 3, 4, 5, 6. Okay? And that's it. Okay, so for this course, I've provided actual work code, both Java and C++, as I've said. And there's one program for sorting, for comparing the different sorting algorithms that we're going to look at. And that's where you'll actually find the code that we just looked at. Okay, so I encourage you to get that sorting code and take a look at it in the appropriate language for you. Okay, let's discuss the two loops again. This time, look a little further into not just how they're set up, but what their purpose is. Okay, so we've already discussed here superficially the outer loop. We can see has a counter, a loop counter I, and it decrements from size down to 1. The inner loop has a counter j that increments from from 1 up to I. Okay, and we've discussed the curly brackets, or rather the absence of curly brackets, already. So, what is the responsibility of the outer loop? Why is it there? What's its purpose? And the answer is very simple. The outer loop is responsible for making multiple passes through the array. Every time we go through the outer loop, we'll be making a single pass through the array. Okay? And then the inner loop is there for the purpose of actually doing that single pass. Okay? Actually doing the comparisons of consecutive entries in the array and then conditionally swapping them. As was indicated earlier, every time we go through the inner loop, each pass through the inner loop will involve comparing two consecutive or contiguous, meaning side-by-side, entries in the array. And then if they're observed to be out of order, it'll swap those two entries to put them in order. Okay? Now, I want you to take a very careful look at the inner loop header, where we see that j goes from 1 up to I. Okay? But when I say it goes up to I, this inner loop terminates when j actually equals I. Okay? So the very last time you go into the inner loop body, the value of j will be I minus 1. The last value of j is I minus 1. That is, say, the value of j the last time through the loop, through the inner loop. Okay, so on this last time through the inner loop, we'll be comparing array bracket I minus 2 with array bracket I minus 1. Okay? And now, of course, that's gonna vary depending on I. So let's think about that. The first time through the outer loop, the value of I will be size. Okay? So in that case, during the first pass, first time through the outer loop, the last entries that get compared in the array will be array bracket size minus 2 and array bracket size minus 1. And that's exactly as it should be, because those are the last two entries in the array. Okay, those are the last two numbers that we have in our list of numbers, right? Because the indexes go from 0 up to size minus 1. Okay, if you go back and look at the code again and take a quick look at the header for the inner loop, you'll see that j always begins at 1. Since j is initialized to 1, it means that every time we do a pass through the array, that pass through the array is going to begin by comparing array bracket 0 with array bracket 1. Okay, and then potentially swapping those two. And that is, of course, exactly as we want it to be. We saw that when the example by hand of sorting an array of 6. Every time we made a pass through the array, we begin by comparing the first two entries in the array. Okay? So now we know that on the first pass through the array, the inner loop, which does the actual pass, is going to begin by comparing the first two entries, and it isn't going to finish until it's compared the last two entries of the array. Okay? So when you think about it, altogether it will have done size minus 1 comparisons. Okay? In stark contrast to that, let's think about the final pass through the array. So here I mean the last time we go through the outer loop. Okay, well, what's the value of I on the last time through the outer loop? And here again, if you go check the header, you'll see that the outer loop terminates when I becomes 1, and so that implies that the last time it goes through the outer loop, goes actually into the body of the outer loop, the value of I on the last pass through the outer loop is going to be 2. Okay? And then because of that, now look very carefully, and I mean this, look very carefully at the inner loop header. You have J initialized to be 1, okay, as always. And you see that it continues as long as J stays less than I. Well, now I is 2. So you're basically going to have J be initialized to 1, and it's only going to continue as long as J stays less than 2. So if you think about it, it means that that inner loop is only going to have there's only going to be one time through that inner loop. Okay? It means that this final pass through the array is going to amount to just doing one single comparison. It's only going to compare array bracket 0 with array bracket 1 and potentially swap them. And that's it. That's all that's going to happen on that last pass through that array, on the last pass through the outer loop. Okay? Well, that's exactly in. So, okay, it does, apparently, that code really does do what we said bubble sort should do. During the first pass, it goes through the entire array. On the second pass, it goes through most of the array, but doesn't bother with the last entry. On the final pass, it just compares two numbers at the beginning of the array, and that's it. Okay? The program works, but, and I can't stress this enough, it's important for you to study it. It's important for you to look at the details carefully and really convince yourself that it does what it's supposed to do. Okay? You know from experience as programmers that if one little thing is out of whack, the program is going to behave erratically and you're not going to get the right results. Okay? Well, obviously, when you're writing your own programs, it's important to sweat the details. But I'm trying to say here that it's also very important when you're studying somebody else's code that you pay attention to the details. Okay, and this bubble sort code is packaged with the other sorting code for the other methods that we're going to look at. There's a C++ and a Java version of the sorting code available at the website. And eventually I'm going to want you to run that so as to compare, as a way to compare the different sorting algorithms. But it might be a good idea to get started early on this. So I encourage you to go ahead and download the appropriate program for you, C++ or Java, get it running, and at least pay attention to the details for the bubble sort right now. Okay. There's an animation for bubble sort that's also posted at the course site. This is provided by another party, and the author of this animation provides his own source code for bubble sort. And I'll point out here that the source code there is, I want to say superficially anyway, it's slightly different than the bubble sort I'm presenting to you. I'm only holding you responsible for my bubble sort, but you are encouraged to look at that bubble sort as well. The difference is in the way the outer loop is set up. So my outer loop has a loop counter I that decrements, whereas this other bubble sort code has a loop counter that increments. But the important thing is what the inner loop does is exactly the same. And so both approaches really implement bubble sort honestly and effectively are equivalent. Okay, so possibly you want to go over the notes again real quick, look at the code in detail. At some point, when you feel like you're ready, I want you to take the self-quiz provided at the website, the course site, and if you have trouble with it, don't hesitate to come back and go over these notes again. And I'm sure that pretty soon you'll get past the self-quiz for bubble sort. Okay.